Hello, my friends. Today we are going to introduce another concept, phasors. And with this concept, we will be able to resolve, um, we will be able to use Ohm's law to resolve the problem of AC circuits. To begin with, let's start with a very simple circuit. The circuit has only two elements, a resistor and an inductor. And the circuit is powered with a voltage source of A cos omega t. This is the sinusoidal voltage. Uh, and the amplitude of the sinusoidal voltage is A. And now, uh, if the voltage is of this form, A cos omega t, uh, this is the time domain voltage, right? Let's highlight it. And we use the Vs of t to represent the time domain of this voltage. And Is of t to represent the uh, time domain of the current. And it's very clear if you have a voltage like this, then the by Kirchhoff's voltage law around this loop, we should be able to find Vs being equals to Vr, and this is a time domain problem, and plus VL of the time domain. This is very normal, right? And uh, the this is the now what is VR? VR is by Ohm's law. You guys would agree that uh, this is going to be uh, uh, I of S T and then R and then plus uh, and you guys would agree that, right? L and then D I of S dt. The conclusion, this is due to the conclusion of Faraday's law. And the left side of the equation is going to be A cos omega t. Uh, so I haven't misled anyone yet. So I'm going to make it clear. Yeah. Too much. What is this? V R T. Then I'm not going to confuse anyone. Now, the solution uh, is very easy. And this is the first order differential equation. We have to guess for a solution. So let's guess IS of, if the voltage source is of a sinusoidal form given by A cos omega t, then it's logical um, to assume the current to be equals to, say, a value, right? This is the magnitude of the current, and then cos omega t plus theta. This is very important. You have to put the theta here because uh, there will be a phase shift, right? Where theta is going to be the phase shift between Vs and Is. Now, if you have shown Is to be B cos omega t plus theta, then you have to find the differentiation because subsequently you need to deal with this. D Is of t is going to be this one, right? B omega. And then this one is cos, and then minus sine. Okay? Now, you have three equations. Equation 1, and this one is equation 2, and you have equation 3 here. And our job is to substitute Is and the time derivative of Is back to equation 1. So I write down the comment here. To 1 and see what we are going to get. And if you do that, then the left side of the equation will remain the same. But the right side will be different, right? The right side, will be R cos omega t plus theta. This is a very complicated solution. And L will be equal to B omega L sine omega t plus theta. There's no easy way to solve these trigonometric equations. The only way that you can do is to break down these two terms. You have to break down these two terms. And if you do that, then what you are going to get for the left side, the same. And what are you going to get for the right side? It will be B R and then cos omega t cos theta and then plus. I'm sorry, it should be minus sine omega t and sine theta. And if you continue this process, then you will end up with B omega L sine omega t and then cos theta and then minus B omega L and sine theta and cos omega t. Wow, this is not an easy process. And at the end, you have to do it very carefully. And in this case, the only thing that you can do is to find the coefficient for cos omega t for both sides of the equation. So if you do it carefully, then you will form two equations. I'm going to erase the upper part because really I don't have enough space to continue. So if I'm going to do here, then I will end up with two equations. The first one is going to be B R and then cos theta and then minus B omega L sine theta. And then we are going to equate the coefficient for sine omega t. And on the left side, it should be 0. And on the right side, then is going to be minus BR sine theta, and then minus B omega L, and then cos. So you have two equations. And if you solve it carefully, very, very carefully, you would end up with B being equals to A R square plus, sorry, B will be equals to R plus J omega L. And actually, this is not the answer for B. But the answer for B will be more complicated. It will be equals to omega and then omega L square. So this will be your answer for B. And in addition to B, you also need to find the solution for theta. And theta, it will be equals to minus tangent minus 1 and then omega L divided by R. The solution process is so complicated. That's why this methodology is too outdated. And we shouldn't use this way to solve any of the AC circuits. And for this reason, we are going to introduce to you another much more elegant method, much better method. The method is so-called phasor. To do that, we have to resolve the circuit in complex domain. Right now, we have the source voltage here, A cos omega t. And our job is to turn this into complex domain. So the solution here, first of all, what we need to highlight, we are going to use phasor to resolve the problem. Phasor. And to begin with, we have to invent another voltage source here. And this voltage source is going to be A J sine omega t. So in other words, the source voltage is not going to be expressed in time domain. It will be in complex domain. So I'm not going to use Vs of t to express it. It's going to be Vs only. Capital letter V and then followed by S. So this will be the source voltage. And then if the voltage is a complex value, then you should expect the current to be the same. It's going to be a complex value. And I'm not going to express the current in Is of t. Instead, the current is going to be Is, capital I, followed by S. And this will be the complex representation of the current. And this methodology is called phasor. And this is also the main ingredient of this video. And to begin with, the first thing that we need is to absorb the current in certain form. If the voltage here is like this, then we simplify the voltage first. Vs is going to be a summation of these two voltage, A cos omega t plus A j sine omega t, and then if we do it carefully, right, then it's going to be j omega t. So it is so clean. This is the expression for Vs. And for this reason, we also need to express Is. Is is going to be so we are going to absorb Is. So let Is to be in this form, B Z J omega t. But do not forget there is a phase shift. So where beta is the phase shift between I and B. Between Vs and Is. So now we don't need any time domain. We only deal with complex domain. So we use this, we move to bracket T to represent the time domain. Now you have the current here, and what is the voltage across the resistor? The voltage across the resistor is going to be Is times R. Everyone know that. And how about the voltage across the inductor? It's going to be L D capital Is, and we have already known that, right? Is is going to be B sine E j omega t plus theta. It will be in this form. So let's do it. Do it very carefully. And it will be J omega L. And then B E j omega t plus theta. But hang on a minute. What is this term? Yeah, we have already defined I of S, Is as B times E to the power j omega plus theta. So why don't we just do this? Now, basically, by applying before going forward, right? Let's examine if there's anything wrong. Okay, everything is okay now. Now, by Kirchhoff's voltage law around this circuit loop, so by Kirchhoff's voltage law, sorry, not V, not C, Kirchhoff's voltage law, Vs is going to be equal to VR plus VL. And for this reason, we can rest assured uh, A E J omega T is equals to these two guys, I S R and plus J omega L I S. But hang on a minute. Haven't we already resolved IS now? We got it. IS is A R plus J omega L, and then J omega L, e to the power J omega L. This is the expression for IS. And if you further simplify it, then it's going to be A R square and then square root of this. Yeah, I'll write down more clearly. It's going to be A and then square root of R square plus omega L square. And then E and then J omega L minus tangent, arctangent, omega L divided by R. So this is all we need for the complex form of the current. The question is, we need to find the complex form is not good enough, right? We need to find the final form. The final form is not the current form, is not the complex form. The final form is the time domain expression of the current. So how are we going to find the time domain of IS? Yes, very easy. We just take the real part. So for instance, the time domain is small letter is of t. Then we have already learned that this is going to be the real part of is. And to find the real part of this expression is very trivial. It's going to be A can you see? It's not, we don't have enough space now. We don't have enough space. Yeah, we are going to write it here. Yeah, we are going to write this here. So I of S is going to be the real part of IS. And what is the real part? According to this expression, yeah, let's clean up this area. We don't need this. It's just A divided by R square plus omega L square. And then we have the E exponential term here. Then it's very logical. Cosine of omega, omega t. Omega t, you put omega t here. And then minus tangent, we just copy it. So this is all. This is your answer for the column. Now, we have already learned the important trick, and we have used phasor to resolve a complex AC circuit, and we finally got the time domain expression, and the time domain expression is just the real part of the complex color. So now, can we generalize a uh, methodology for AC circuit? And most of the thing is already well known. For instance, in this case, we have J omega t, e to the power J omega t in both sides. We don't need that complicated solution. And another problem is we also have, in addition to inductor, we also have capacitor. So now we are going to apply what we have learned in so far, and we are going to come up with a methodology to resolve the problem. Now, let's erase the whole board. And do not forget that um, VS is going to be, no, IS is B exponential J omega t plus theta. Where no need, right? Yeah, we need it. Right? Where theta is the phase difference between VS and IS. So now we are going to use Ohm's law to resolve this AC circuit, and we know that in Ohm's law, the voltage across the resistor is going to be um, to be VR is equal to R plus IS. We know that. And we are going to introduce another concept. The other concept is called impedance. And in this case, R is a resistance. And instead of calling it resistance, we add another name for this resistor. And this one is so-called resistive impedance. And from now on, we are not going to use resistance only. We use a more generalized terminology, impedance. And you have resistor. How about the inductor? So inductor, we have the similar treatment. We know that the VL is going to be L dis dt. So now let's substitute is according to equation 1 to see what happened. So L d t, and then the expression here. Now, if we do it carefully, then we will end up with J omega L, and then B E to the J omega T plus theta. But hang on a minute. B times E to the power J omega T plus theta is actually IS. So in fairness, right, this is going to be J theta L and then IS. And we have a very complicated expression here, yeah? J omega L and then times IS. Let's call this bracket term inductive impedance. Inductive impedance. Now, this circuit is overly simplified. We have only resistor, inductor, but we don't have capacitor. So let's add one. Let's add one. And we are going to generalize. We are not in the position to solve this circuit again. Instead, we are going to come up with a methodology. And this methodology is called Phasor. And the capacitance is C. And the voltage across the capacitor is VC. And now we are going to find the voltage for VC as well. And capacitor. And we are going to find the voltage for the capacitor. And what is it? Yeah, the voltage is going to be 1 over C. And then the IS and DT. And if we substitute IS into this expression, this equation, then we are going to get B J omega T plus theta and dt. So here I'm going to erase this term because it causes confusion. And now, if you do it really, very carefully, you will end up with a term like IS J omega C. So this is the beauty of the complex number. So now it's fair for us to summarize what we have learned. We have learned the resistor, and we know the voltage across the resistor is given by IS times the resistive impedance. So this is the number one point we have learned. And we have also learned the voltage across the inductor. The voltage across the inductor is given by VL and then times this much. So we are going to highlight it as well. This is what we have learned. And more importantly, we have learned, yeah, sorry, uh, learn this one. So now, how about this? We are going to invent another variable, so-called impedance. And in this case, the impedance of and this expression will become uh, VR is equal to IS, and then the resistive impedance. And in here, we are going to do something similar. And the voltage across the inductor is going to be called, uh, is going to be IS, and then ZL. Uh, ZL is the inductive impedance. And in here, we are going to do the same for the capacitor. And the capacitor is called VS, sorry, VC, and equals to IS, and then ZC. So this is going to be the expression for the capacitor. So now, it's fair for us to say this. Well, whenever we come across with the circuit, we just need to replace it with the impedance. And we have a resistor, inductor, and capacitor. And we also know that the impedance of them is going to be resistor, right? Is easy, right? R, and the inductor, J omega L, and the capacitor, 1 over D. So with this in mind, we can use this formula to solve the AC circuit problem. I presume you guys are ready. You have already have got enough information about the derivation of this resistor, inductor, and capacitor, and also the impedance of this. Right now, I'm going to apply what we have learned to a circuit example. Let's say we have a circuit. We have a circuit, something like this, right? Uh, uh, we have a circuit uh, powered by a household electricity supply. And this circuit is very simple. You have a resistance. The resistance is going to be say, 5 ohm, and the inductor. Inductor is going to be um, uh, say 100 millihenry. And we also have a capacitor. The capacitor it can be any value, eh? It can be a large value, say uh, 1 millifarad. And because this is a household electricity supply, then the voltage input should be 220 volts. And the frequency, very important. The frequency is going to be 50 hertz. And in some country, this should be 60 hertz. So now we need to work out the impedance first. We have already done the analysis, right? Resistor, uh, uh, in this case, the resistance here is going to be R plus 5 ohm. Yeah, the inductor is going to be the impedance for the inductor is going to be J omega L. And what is omega? Omega is equals to 2 pi F. F is 50 hertz, and L. And if you do it carefully, you will end up with, let me do that, 250. We will end up with minus, actually, 31.4. And if you do it carefully for the capacitor, the capacity inductance, sorry, capacity impedance is going to be 1 over J omega C. And if you do it carefully, then you will end up with 1 over J 2 pi 50. 1M. And the value is going to be is P.18 minus J P.18. So now the question is, what is the current? And I have already told you, right, to solve this kind of problem, you have to use complex number. And instead of beginning the problem with I of t, you have to use I, which stands for the complex value of the current. And according to here, yeah, the voltage is going to be 200 and then 0 degree. So this is the voltage for the source. And we are going to get the current. The current is going to be, say, yeah, that's okay. The voltage divided by the total impedance. And we have already got this, right? VR plus VL plus VC. So this is the way how we solve the problem. And if we do it carefully, we will you will have 220 5 plus J31.4 minus J3.18. The answer is going to be very simple, right? Let's try it. I wrote down this question. 220 and I. Okay, the column is going to be minus, sorry, 7.6 68 ampere, and then the angle for this current is going to be minus 80 degree. Now you have got the complex current. But this is not the final answer. The question in this case asks you for the time domain current, and as I already mentioned to you, right, the time domain current is going to be the real part of I. And if you do it carefully, then it's going to be um, 7.68 cos omega t and then minus 80 degree. So this is the answer by direct inspection. Okay, thank you. If you have any question, please leave your questions in the comment section. I will be happy to resolve it. Thank you very much.